Hello, this is Professor Keen, and welcome back to my course on electricity, magnetism, and light here at Wisconsin Lutheran College. We have been talking about the work of Charles Augustin Coulomb, his work on the law of electric force. You'll remember last time we talked about the apparatus, the experimental apparatus he designed, and then the experiments he carried out, and the law of electric force that he arrived at. Let me jog your memory, remind you of what we have been talking about. On page 70, there's a diagram of the experimental apparatus, which consists of the essential components are a wire that's hanging down a tube, and suspended from that wire is a cross beam, you might call it, and on one side of the cross beam is a small ball. That ball is charged up by putting it into contact with another ball, and those two balls repel each other, and when they repel each other, the one movable ball swings around and is held eventually at some position or some angle of rotation by a torsion wire. So if you were to look down the apparatus from the top, so I'm reminding you of what the apparatus looks like. So if you look down at the apparatus from the top, you've got one ball right here, and that's fixed at a particular location. That's the fixed ball. And the other ball, originally in contact with it, swings away from it when they repel each other. So let's say it's over here until it gets to some angle. And again, it's kind of on this rod like this, or this is a top view. This right here is the torsion wire. I know there's a counterbalance, a counterweight over here. I'm omitting that for the sake of simplicity of this diagram. This ball is attached to this torsion wire by an insulating rod, and it moves away like this. Now, why does it move away? Well, because these balls are charged up and they have repulsive forces acting on them. So this ball, having some charge, is exerting a repulsive force. I'll draw a little arrow right here. I'll call this the force of repulsion acting from this ball on that ball. And that's really what Coulomb is studying. Of course, this ball right here is pushing back on that ball as well, but I'm not going to draw that arrow because I'm interested primarily in the force of repulsion on this ball. Now the question is, how do you measure this force of repulsion? That is what Coulomb would like to do. Well, you basically twist this torsion wire in this direction. There's a micrometer on top of this. You twist it, and when you twist it, there's that wire twists, and this rod here pushes the ball back to some location. And by how much force this torsion wire is pushing it back, that provides a measure of the repulsion force right here. Because after all, if this was the only force acting on that ball, it would just fly away from the fixed ball. The only thing that's holding it in place is the force exerted by the torsion wire that's holding it back. So by measuring the force exerted by the torsion wire, it gives you a measurement of the repulsive force between those two balls. And what he finds, you might recall, is that repulsive force that's required to hold it in place depends on the angle theta between them. So as the balls are closer to one another, that repulsive force is bigger. The farther they're away from one another, the weaker that force is. Okay? And let's remind ourselves what the data table looked like. He was measuring the distance between the charged balls, or the charged spheres. And the units he's using for that is angle theta. I realize angle isn't technically a distance, and we'll come back to that in a moment, but the bigger the angle, the bigger distance they are away from one another. And then he's also measuring the force of repulsion between those two balls. Technically, he's once again measuring the force that's exerted by the torsion wire, but that provides a measure of the force of repulsion. And this is measured in the angle of twist in the wire. So how much you have to twist the wire in order to keep that ball in place. And let's remind ourselves what his data was. So some of his data points, he said when there's an angle between the balls of 36 degrees, well, there is a force corresponding to 36 degrees of twist in the wire. Then by twisting this wire more in the clockwise direction, you could push that ball in to a distance of about 18 degrees. But how much did you have to twist this in order to do that? Well, you had to put 144 degrees of total twist in the wire, right? And then if you twist this even more, you can reduce the distance to a distance of 8.5 degrees. And when you did that, if I remember correctly, there was 575.5 degrees of twist in the wire. And the point that he made, you might recall, is that every time you halve the distance, you roughly half the distance here, well, how much force, how much torsion is in the wire, how much force, you have to quadruple the amount of force, and from here to here, you're quadrupling the force. And remember, the upshot of all this is that the force of repulsion between those balls was proportional to 1 over the distance between them squared, right? That is called an inverse square law. Inverse square law. And just to remind you sort of how this works out, let's suppose at some particular distance, we'll call that, so for example, if you're at a distance d1 between those two balls, and if you plug that in to this formula, you'd get a force 1 would be proportional to 1 over d1 squared, okay? But let's suppose you have the distance, so now it's half of the distance d1. Well, what would the new force be? This is, let's call that distance 2 is 1/2 of the distance. Well, when you bring it to 1/2 the distance, what is the force going to be? We'll call it force 2. It's 1 over d2 squared, right? It's proportional to 1 over d2 squared, which is saying, well, d2 is 1/2 of d1. This is a proportional 2 sign, by the way. So it's 1/2 of d1 squared. And that is, well, if I keep going like this, 1/2 squared is 1/4 d1 squared. And notice that 1 over d1 squared was the force that was exerted originally. So, and I'll take this 1/4, move it to the numerator. So you get 4 times 1 over d1 squared, which is 4 times the original force, 4 times force. So if you have the distance, you get 4 times the force that you originally had. So that's an example of how this illustrates how this law right here captures the data up there. Now I want to say 2 other things before we finish up with this discussion of Coulomb's experiment. First of all, keep in mind that he is measuring the distance between these balls in angle. And strictly speaking, when you do this, when you reduce the angle by 1/2, you're strictly not having the distance. And so let's think about that for a moment. It's because the distance between these is technically the chord of that arc. So if I draw a diagram right here, let's suppose originally they're at some distance away from each other. I'm going to draw an arc like this. Okay, this is the length of this rod like this. And let's suppose they're at some angle like this apart from each other. Here's the ball right here, and here's the ball right there. And you might say, well, what if we have the angle? So I'm going to draw another angle right here. This is supposed to be half the angle. Strictly speaking, the original distance was the chord right here. That's the original distance, d1. But when you have the angle, you're bringing it to right here. Now the distance is this chord right here, which is technically not exactly half of the original distance. In fact, it's a little bit more than half of the original distance. You can probably see that from this diagram. Half the distance would be from here to here, but now it's from here to here, which is it's a hypotenuse right there. It's a little bit more than half the distance. So strictly speaking, when you go from this angle to this angle, the distance between these balls is not half as big, it's a little bit more than half as big. But as long as you're dealing with fairly small angles, then this is a good approximation. And you can see here that he's running into some problems here. It goes half here, and this isn't exactly half right there. So we'd have to, if we're going to do a systematic uncertainty analysis on his experiment, we'd have to take into account the fact that having the angle technically does not have the distance between those balls. So that's one point I'd like to make. Another point that I'd like to make is the force of repulsion is being measured in angle of twist. Now, you might complain about this because strictly speaking, an angle isn't a force, right? But the point he's trying to make is that the angle of twist provides a measure of the force. Okay, but if you wanted to convert this to pounds or newtons, you would have to calibrate this torsion wire. So in other words, to measure the force of repulsion in conventional units, one would need to calibrate the torsion wire. How would you calibrate the torsion wire? Well, one way to do it is if you were to apply a known force to it to twist the wire, and then figure out how much twist of the wire corresponds to what force. So let's suppose you were to apply 1 millinewton of force and find out how much the wire twists. Let's suppose it twists by 1 degree when you apply 1 millinewton of force. Not using charges or anything, you're just using some other scale. And then you apply 2 millinewtons of force, you get 2 degrees of twist in the wire. And 3 millinewtons of force, you get 3 degrees of twist in the wire. Then what you have is you have a calibration for every degree of twist in the wire that corresponds to 1 millinewton of force, for example. And that is precisely what Coulomb does on the next page, on page 72. He talks about how he calibrated this wire and how he doesn't use newtons. After all, the Newton wasn't even, I guess Newton hadn't done his famous experiments yet, and the Newton system of units for force wasn't in effect at this point. He measures force in grains, and a grain is a measure of weight, and a weight is a measure of force. So this, by the way, grains are still used for people who make firearm shells, right? You have 230 grains of gunpowder in a particular bullet. And so that provides a measure of the weight of the gunpowder. And from what I've read, the dentistry also uses grains when measuring amounts of gold for fillings or other kind of materials for fillings. So anyhow, what Coulomb does in the second paragraph here on page 72, he explains the calibration of his torsion balance by saying how many grains of weight correspond to how many degrees of twist. Okay, and when we do this in lab, by the way, this week, we're going to take a torsion balance and we are going to have to perform a calibration on the torsion wire. We're going to set the balance on its side and stack tiny milligram weights on the ball and see how much twist that makes the torsion wire undergo, and that's going to provide our calibration so that we can measure force actually in newtons. Okay, tell you what, why don't we stop there? I think we've finished our discussion of Coulomb's law of force, and next time in the lecture we are going to begin with the work of Hans Christian Ørsted.